Okay, it's for real this time. Anyways, I took the quiz. I got 5 out of 5. It's fine. But the one about the hydroboration, I think is just wrong. I don't think that you can use this and have it work. I'm pretty sure you have to use what is it called? 9 BBN or something like that. I think you have to do this. Okay. All right, so now I'm just doing physics, I think. Let's see. What else do I have to do? This one. Yeah, I want to do a couple problems from here, but I think it's and this one's annoying because one I have to use Chrome. So I'm just going to do the physics homework then. I don't even remember what problems I need to do. I think it's here. Okay. Wait. 9 BBN gives you the anti-Markovnikov? That doesn't even make sense because you're not even adding anything, right? I don't think that's right. Because it's an oxidation reaction. It's not like... I don't know. I'd have to look at the mechanism. Honestly, he's probably right. Okay. All right, chapter 14, problem 15. It's called Survey. So these are concept questions. I think it's the... Wait, which questions are we doing? I don't... Does it even say what questions to do? Starting at page 438. Okay, so these. All right. Okay, D, H, W. D is equal to 2 meters. H is equal to 1.00 meters. W is equal to 2.00 meters. Determine the magnitude of the force the water exerts on the hatch. F of water on wall on the hatch. Okay, so pressure is equal to force over area. That's the most important thing. And that's equation 1. Equation 2 is F is equal to pressure times area. And 3, a force element is equal to the pressure times an area element. And now an area element is equal to the width times dy. Now 5, the pressure is equal to so the pressure is going to be equal to the depth. So what we're going to do is we're going to call y equal to 0 on the bottom. So this is y equal to 0. The pressure is equal to the density times gravity times the depth, which is going to be d minus y. So when y is 0, the pressure is the highest. Dude, I have not been able to think about doing anything but chemistry these whole past weeks. I mean, this stuff is just not inspiring me. Okay, so now we can combine the equation. So equations 4 and 5 go into 3, and we get that dF is equal to rho g d minus y times the width and the vertical element dy. Okay, so then we take, so this is equation 6. We take the integral of both sides, and we get f is equal to the integral. First, we can factor out rho gw. Then we're going to get the integral from 0 to little h of d times dy minus integral from 0 to h of y dy. So this is going to go to dh, and this is going to go to h squared over 2. Is that right? That something seems wrong. I'm pretty sure that's wrong. I'm pretty sure it's supposed to be h squared minus h squared over 2. Because you're going to get dy evaluated h0. I mean, this seems right, though. So then, so this is the force. So this is 7, 8. Then we plug in. So okay, so this is annoying, but 1,000 kilograms per meter cubed times 9.81 meters per second squared times the width, 2 meters. Okay, then it's going to be times dH. D is... well, whatever. It's 2 meters times H, which is 1 meter. Oh, but this is minus 1 meter squared over 2. Actually, wait. Let's see if I can just do... I don't know what the easiest way to do this is. I prefer to use a real language rather than just type... I mean, honestly, this would be the easiest thing. It's just... I don't think that's right. So wait, let's see. Okay. I've written this so many places now, but I don't want to do calculation. I just want to... I gotta do this shit. Why doesn't... How do I set theme persistently in Helix? Bro, really? No, but that's stupid. Okay, yeah, let's just do this. All right, so config open. Oh. Wait, control slash doesn't comment things out? All right, I don't actually care. Okay, now it's a light theme. Okay, so D equals 2.00 meters. H equals 1.00 meters. W equals 2.00 meters. And then we have, you know, P is equal to F over A. This is equation 1. Then we have F is equal to PA, which is equation 2. We have DF is equal to PDA, which is equation 3. Okay, then we have the dA is equal to W dy. And then we have that P is equal to the density times the the gravity, the force of gravity, and then the depth, which should be d minus y. Y equal to 0 at bottom of tank. Okay, so then we do 4, 5 into 3, and we get df is equal to rho g d minus y times w dy, and that's equation 6. And then we integrate, and we get f is equal to rho g w int d dy minus int y dy bounds, or wait, let's do this. Equation 7 bounds y in 0 to h. Okay, so then we get f is equal to rho gw d h minus h squared over 2. Then this is equation 8, plug in values. So rho to 1,000 kilograms per meter cubed. G equal to 9.81 meters per second squared. And then D, H, and W. And we get that F is equal to 29.4 kilonewtons. And then I have to do this. What, GG... I actually hate these editors, but I hate opening VS Code. This is problem 1. Because it's so annoying to... Actually, can I just select things like this? Oh, that's actually nice. Okay, I can select things like this. So I can just go like this. Oh, what did I do? Oh, because Control C is the comment? Oh, really? Fun. I think I just have to do space Y. Okay. So, all right, so this is my answer to this problem. And I am trying to figure out if I did it right. Because I remember I solved it a different way and I got that this is H minus Y. But I don't think that's right. I think it's... Yeah, this I think is right. And then let me just look at her... Start with equations and symbols, number your equations, reference your equations, solve for the requested variable and symbols, make substitutions, attach units using SI consistently, compute the final numeric value, put a box around it, or an X column section. Okay, that I kind of did it. Okay, so that's what was that? Oh, jeez. What was it? GE? How do you... But G... E goes to the last line, but how do you go to the last? I waste so much time doing bullshit, dude. GE goes... I think what you're supposed to do, dude, why do I care? Okay, 14 point, what's the next problem? Oh, wait, we didn't do this was A. So, this is A. And this is going to be B. We didn't actually finish. So the next part is find the magnitude of the torque exerted by the water about the hinges. Okay. So that's a little harder. What the fuck? How did all this ink get on me? What? Alright, I don't... How did that even happen? I'm covered in ink. Okay, so now what we want to do is we want to find df. We have df. So what is r? R is going to be h minus y. So it's going to be h minus y df. So then, torque is equal to r, or d tau is equal to r df. Okay, so first off, tau is equal to, r vec cross f vec. D tau is equal to r vec is there a way to do Unicode in here? I don't think so. I doubt it. Cross df. So this is like equation 1. I'll just number them for the whole problem. But RV, oh yeah, and we could do d tau is equal to RV df sine theta. But theta, okay, so I'm going to say this is 12. And then r is equal to h minus y. So then we're going to plug in 6 and 13 into 12. And we're going to get that the torque is equal to the integral from 0 to h of h minus y times df, which is, rho g w d minus y dy. Okay, and now I'm going to write that out on paper and do the rest of that. And then we'll fix it up. So the integral from 0 to h of h minus y rho g w d minus y dy. All right, so we can pull out this, and then we get h minus y d minus y rho g w. Okay, this becomes dh minus hy minus dy plus y squared, all dy. That's a freaking annoying integral, I think. Okay, so it's going to be dh squared minus, so it's going to be hy squared over 2, which becomes h cubed over 2, minus dh squared over 2 plus h cubed over 3. Okay, so I think that the end of this integral is rho gw times dh squared minus h cubed over 2 minus dh squared over 2 plus h cubed over 3. All right. So then we just plug in rho g w d h, and we get oh wait, actually, just selecting it do it, but it's puts it in the wrong register. So you have to get it into register plus. Okay, so 16.4 kilonewton meters. Okay, let's see if the book has the right answer, because I just want to not rely on this, but that's what I got, and I feel like that makes the most sense. Chapter 14, number 15. 2.94 and 1.63. Okay, yeah, that's good. All right, so that was pretty easy, actually. I'm not too stressed about that. What's the next problem? 39. How many cubic meters of helium are required to lift? Let's see, how well does this copy in here? I feel like this is going to copy in pretty bad. Yeah, see, yeah, because it's for some reason PDFs encode like like I don't know what it is because that's not OCR, right? That's like some weird thing, and I don't understand that. Like, why does copying the equal sign? Yeah, I've seen that so much. All right, so what? So whatever. Dude, I hate doing these homeworks like this. It was so nice last quarter. No homeworks, just do the quiz. It was stressful, but it was nice. Cause now I'm like worried about like how nice does my homework look, especially when like the teacher puts in some crazy shit like this, like you better do it the right way. You better do it the way I like. All right. Okay, so we have a balloon with a 400 kilogram mass attached to it. The density of helium is given as constant at 0.179 kilograms per meter cubed. And so then the volume of balloon is constant. And the density of air decreases with altitude. Okay. Rho air is equal to P0 atmospheric pressure times exp of minus Z over 8,000. With the unit of Z is meters. Okay, so, and then P0 is equal to 1.20 kilograms per meter cubed. So we just plug in we plug in 8,000, that goes to 1, so e to the minus 1, or so it's going to be 1.20 times exp of minus 1. So it's going to be 0.441 kilograms per meter cubed. Okay, so what we want, so basically this is just balancing the buoyant force and the weight. So we have W and B is the free body diagram. So W is equal to 400 times, G. And B is equal to the density times the force of gravity times the volume displaced, which is equal to the, displaced. And vol balloon equals vol displaced. So that's good. So now the next step is to okay, so now we can just equate the W is equal to B, and then we solve for the volume, so we get 400. Or actually, let's just leave it as W. So rho GV is equal to W. V is equal to the weight over the density times gravity, which is equal to 400 G over and this rho is the rho of the fluid, which is going to be air. G's cancel, and we're gonna get 400 kilograms over rho, which is going to be kilograms meter cubed, and we're going to get our result in meter cubed. So that's good. Okay, so I'm ready to do the problem. So basically, so let's type in the parameters first. 179 kilograms per meter cubed. Rho air is equal to rho air 0 times x of minus z over 8,000, and with z in meters, and then rho air 0 is equal to 1.20 kilogram per meter cubed. So that's all the parameters, and then we plug in rho air of 8,000 is equal to 0.441 kilogram per meter cubed. So now that's all the calculations. The free body diagram is basically weight of payload and buoyant buoy. Yeah. Buoyant force. So here we go. Weight is equal to 400 kilograms times G. B is equal to rho air G vol displaced. So wait, 1, 2, vol displaced equals vol balloon. Fully submerged case. Okay, and what's happening here is that so now we have that weight plus let's just think about the direction of the vector. This will be minus. This will be minus. So G is minus. I actually don't know. I'm just gonna do this. And so then we're gonna get so then we get equation. I actually don't know why we need this. I need a review. I don't, because in this case, it's fully submerged, so I don't even think I need to put that in there. Well, so we're going to plug in 2 into 4, and we get, weight is equal to rho air GV. So V, I hate this numbering shit. V is equal to weight over rho air G, and then we're gonna plug in 1 into 5, or so this is 6, and we get just 400 kilograms over rho air, which is equal to 400 kilograms over 0.441 kilogram per meter cubed is equal to no wait, is it divided? I think it's divided. Okay, yeah, I fucked this up. Okay, because the helium also weighs something. So we need to figure this out. So the weight of the helium is going to be equal to the density of helium times the volume times G. And this is going to be negative. We're going to say G is directed downwards. So this is a minus. And then also minus 400 G for this is okay, the weight of helium and the weight of the payload. And then the buoyant force is equal to positive and the buoyant force is equal to the displaced weight. And that's going to be the density of air times the volume of air. And I don't think that there's a gravity involved in that. Is it? Okay, it is. But well, because that's a mass. Okay, times gravity. All right, that's good. Hold on, I'm gonna be right back. Okay, so I think it's probably best to, before I even start the problem, oh wait, how do you do it? How do you delete a line? Okay, okay, why doesn't down work there? Okay, so we're gonna get, so this is equation 5, 6. So we're gonna get minus 400 minus rho he v plus is or actually let's do this. 400 plus rho he v is equal to rho air v. So then we get this minus rho he v fuck me. Oh my god, dude. Okay, so um so I think that that's it. So it's going to be 400 divided by you know, 0.441 minus 0.179. So it's actually uh, all right, good. Thank God I was getting pissed off. Okay. Called A. This is called capital A. This is V. And this is F. A hypodermic syringe contains medicine with a density of water. Okay, so this has rho H2O. The barrel of the syringe is cross-sectional area. Okay, so capital A is equal to 2.5 E minus 5 meters squared. Little a is equal to 1 E minus 8 meters squared. In the absence of a force on the plunger, the pressure everywhere is 1 atm. And then F is equal to 2 newtons. Okay, so I think what it's saying is that there's 1 atmosphere of pressure going this way. So that when we do the Bernoulli's equation, so it's Bernoulli's. So we get P1. So the first thing to start with whenever you're thinking about Bernoulli's equation is just to derive it, because it's a super simple equation. So what is it? It's that the work is equal to the change in energy of a system. So if we imagine our like pipes, and the pipe is changing in area, but it's also changing in height, and then we set the bottom pipe equal to y equal to 0, and the second pipe equal to, or let's say this is y equal to y1, and this is y equal to y2. And then this is A1 and this is A2. So we have areas, and now the density is the same, but the pressure is not. We consider a parcel of fluid with delta X. And then we have V1 and V2. So what do we know? We know that the pressure can change, we know that the height can change, and we know that the velocity of a parcel of fluid can change. So if we just consider the velocity changing, then we're going to have some kinetic energy in the bottom, which is 1/2 mv squared. And then this is v1. And then also 1/2 mv2 squared. And so, but here's the thing, though, is that the mass is going to be the volume times rho. And because of, what do they call it, the continuity equation? We've only, and that parcel of fluid has traveled in delta t time. So we get that V1 is equal to delta x over delta t. And the continuity equation says that the parcel of fluid at the bottom that we're considering, as it's moved to the top, it's the same volume. So the area times the velocity and the area times the velocity at the top is the same. And all that's to say is that this is a is it the velocity or is it the displacement? I've remembered that it's the see, I have gaps in my understanding. We start off with the idea that we have the work done is equal to the change in energy, and the system is the parcel of fluid. Now, what is work? Work is, a change in energy, but more specifically, it's a line integral of a force along a displacement. And so this displacement is going to be dx, and this force, the force is probably the pressure times the area. So now, what is pressure? Okay, so we have work is equal to work is equal to the pressure times the area times the displacement of delta x. But A delta x is equal to volume, so work is equal to the pressure times the volume. So now, if we consider the delta work, right, I believe, net work done on the system will be it should be is equal to the work at the minus the initial work, which is really kind of like a wait, is Newton meter a joule? So anyways, this is going to be the pressure at the end times V minus pressure. Wait, I did something wrong. That I don't understand. We got to go back to the book. So let me duplicate this again. Is it this? No, it's not this. It's not that. This is what I'm trying to find. Why is it that? Oh, yeah. Because you have to remember that the force is in the other direction. So we should get the net work done on the segment by these forces in the time interval delta t. Let me try to read it again, because this book is so dry, but it's got to sink in at some point. Consider the flow of a segment of an ideal fluid through a non-uniform pipe in a time interval delta t as illustrated in the figure. This figure is very similar, but which we used to develop the continuity equation. We've added two new, which by the way is, yeah. The forces on the outer ends of the blue portion of fluids and the heights of these portions. The force exerted on the segment by the fluid to the left of the blue portion in the part A. um, is it the sum? It's the sum, right? That's not even right. It messed up on this earlier. All right, so I kind of. So where did we go from there? Oh, okay. Let me get my phone charger. Okay. So now that we've derived Bernoulli's equation, we can understand that in the problem, well, first off, let's write down the parameters. F1 is equal to 2.00 newtons. A is equal to 2.5 E minus 5 meters squared. A is equal to 1.8 E minus, 1 E minus 8 meters squared. And F2 is equal to 1.00 newtons. Atmospheric. I think that's what they said, right? Or no, the pressure. And y1 equals y2. So then all we have to do is say that the pressure, so the pressure on this thing is going to be F times A, right? So P1 is just equal to F times A, which is equal to, like 2 newtons times an area. Wait. No. What am I talking about? The pressure is the force over the area. 2 newtons divided by whatever it was, 2.5 E minus 5 meters squared. So P1 is equal to 2, F1 over A. P2 is equal to, and what is the force there, though? I think the force we don't need. We just need P2 is equal to 1. Yeah, so we're given that. So then we just apply, P1 plus 1/2 rho, which is water, and then V1 squared. I didn't actually read this section. I don't think that's anything. How do you know the velocity of it? Oh, I think I know. Um, oh, I know what to do. Hold on. Do I? Yeah, I think I know what to do. You plug in the continuity equation into Bernoulli's equation. So, okay, so okay, so let's figure this out. So we're gonna get P1 plus 1/2 rho A2 squared over A1 squared V2 squared is equal to P2 plus 1/2 rho V2 squared. Okay, so then you get like, da da da. I think it's V2 squared is equal to 2 times. So then we should be able to solve this, right? Because now, is there a way to split this out? Oh, okay, wait. P2. Okay, so we're gonna get 2 times P2, P1 minus P2 divided by rho is equal to 1,000. Okay. P1 minus P2 divided by rho times times 1 minus, and this is gonna be a squared over a squared. Okay, so that's obviously wrong. I think you can just take the absolute value. I'm pretty sure you can just take the absolute value. No, you can't do that. Oh, that's actually so annoying. So you have to manage with this. Oh, okay. I mean, this is still right. It's just that Okay. Okay. Yeah, that one's pretty good actually. Not bad. All right. Okay. What's the next problem? 70. With reference to the dam studied in example 14.4 and shown in 14.5, show that the total torque exerted by the water behind the dam about a horizontal axis. Show that the total torque exerted by the water behind the dam about a horizontal axis through O. Show that the effective line of action of the total force exerted by the water. Okay. Did I miss any part B's? Okay, I don't think I did. For once in my life, I have someone who needs me. All right, so let's draw this dam. That's a torque. Yeah, that was easy. We already did that one. 1/6 rho g w h cubed. So that was easy. And now it's saying, show that the effective line of action of the total force exerted by the water is at a distance 1/3 h above O. So we know. So first, what they're saying is find the amount of the force, and then say how far from the axis do we need to get this torque. So the force is rho g w h y over 2. So this goes to h over 2. No, this is just h squared minus h squared over 2. So we get rho g w h squared over 2. So force is has a magnitude of rho g w h squared over 2. So then rf is equal to tau is equal to, implies that r is equal to 1/3 h. Okay, that is easy. Okay, so let's just do this. So what is it? 13 or 14.70. All right, so dam with height h, width w, y equal to 0 at bottom. So then P is equal to force over area. That's just the definition. So then force is equal to pressure times an area. So then dF, a force element, is equal to pressure times a small area. So then dA is equal to the width times dy, because that's because pressure changes with depth. So then P is equal to rho g y, but it's really, depth, which is equal to rho g h minus y. Okay, so now we get that dF is equal to rho g w h minus y dy. So then you integrate and you get that F is equal to rho g w h squared over 2. Okay, but to find the total torque about the axis at bottom, d tau is equal to r cross df. R is equal to y. So then, so this is equal to y cross y df sine 90, because the force is always normal to the parcel. So so then is equal to y df. So then tau is equal to int from 0 to h of y. We'll just do this. Rho g w y h minus y dy. You end up getting rho g w h cubed over 6. And so solve for r, which is y. So then, y times, or let's say x times rho g w h2 over 2 is equal to rho g w h3 over 6, implies x is equal to h over 3. All right, so that was pretty simple. I'm pretty sure this next one's a little bit more involved. 81 or something. Okay. Okay. Oil having a density of 750 kilograms per meter cubed is then poured into the right arm and forms a column of 5 centimeters high. Determine the difference H in the heights of the two liquid surfaces. Okay, so okay, so what do we know? We does it say that we're allowed to take the Oh, here we go. Take the density of air. That's what I thought. Let me get a hoodie. Um So this is what's confusing me. So the pressure here and the pressure here are both P0. Now, the pressure will increase linearly given by the density of the oil. Then, once we reach this boundary, it will start increasing with a different slope linearly given by the density of the water. So we could consider the equation as the pressure is equal to P0 but what is confusing to me is if this is P0, so we're trying to find H. Why the hell does it come blurry like that? I don't like that. So I think I know how to do it, but I'm still trying to work out the conceptual part of it. I think that the pressure, let's say here in the water, will have the same pressure at the same depth. Or does it even? Because it. But so that means the pressure all along here is the same as here. But I don't see how that's possible. So the pressure here and the pressure here are not the same. But the pressure here and the pressure here are the same, and the pressure here and the pressure here are the same. That's what it seems like to me. So what I think it's going to be is rho without a subscript is water. So rho G H minus or L minus H plus P0 is going to be equal to P0 plus rho oil G times L. That's what I think it is. No, wait, what am I doing? I knew it was going to be like, this is kind of what I expected. Yeah, 1.25 centimeters. Kind of makes sense. All right. So, but pressure is really weird. Okay, so let's just write it out. So, okay, I need to go do something. I'll be back. All right. I'm back. So what is part B saying? Part B was confusing to me. Part B is saying that the right arm is shielded. So presumably stays at a pressure of 1 atmosphere. So wait, what does this mean? This means like if you blow air across the top of this thing and the water increases, it was as if you pushed this down. What does that mean? That doesn't make any sense. That's impossible. Oh wait, makes the pressure just above the left water surface drop. Is it sealed or is it open? The fast moving air of the left side lowers the static pressure there. The fluid rearranges until pressures match at the same depth. So now the pressures here have to be the same. And what does it say? Find the velocity? Yeah, okay. But how do you, is that from this section? Jesus. Okay. This is actually pretty sweet. Yeah, Bernoulli's equation is pretty tight. Okay, so anyways, then the other thing that we need to do is we need to L was 0.05 divided by 1.2. Okay. So wait, is that it or is there more? Okay, that's it for this. So now we got to do chapter 16. Honestly, bro, this thing was boring the hell out of me. I think I wasn't getting it. Small elements of water in contact with the object as well as all the other water elements of this pond's surface behave in the same way. That is, the water wave moves from the point of origin to the shore, but the water is not carried with it. The world is full of waves. The two main types being mechanical waves and electromagnetic waves. In the case of mechanical waves, some physical medium is being disturbed. So, mechanical and EM waves. Mechanical needs medium. EM doesn't. In this part of the book, we study only mechanical waves. Consider again the small object floating on the water. We have caused the object to move at one point in the water by dropping a pebble at another location. So wave transfer energy but not matter. All right. Waves don't die. Let me crash on a moment. I don't need an army, no lie. Waves don't die, baby. They ain't granting a moment, baby. I know, I know. Okay. Propagation of a disturbance. The introduction to this chapter alluded to the essence of wave motion, the transfer of energy through space without the accompanying transfer of matter. In the list of energy transfer mechanisms in Chapter 8, two mechanisms, mechanical and electromagnetic radiation, depend on waves. By contrast, in another mechanism, matter transfer, the energy transfer is accompanied by a movement of matter through space with no wave character in the process. All mechanical waves require some source of disturbance, a medium containing elements that can be disturbed in some physical mechanism through which elements of the medium can influence each other. Okay. Okay. So a source of disturbance, a medium containing elements that can be disturbed, and then a mechanism for which the elements in the medium can influence each other. That makes sense. One way to demonstrate wave motion is to flick one end of a long string that is under tension and has its opposite end fixed as shown. In this manner, a single bump called a pulse is formed and travels along the string with a definite speed. The hand is the source of the disturbance. The string is the medium through which the pulse travels. Individual elements of the string are disturbed from the equilibrium position. The elements of the string are connected together so that they influence each other. The pulse has a definite height and a definite speed of propagation along the medium. The shape of the pulse changes very little as it travels along the string. We shall first focus on a pulse traveling through a medium. Once we've explored the behavior of a pulse, we will then turn our attention to a wave. Bro, I'm gonna go in the sun. Well, it's so cloudy. It's not even gonna be sunny. Whatever. We will then turn our attention to a wave, which is a periodic disturbance traveling through a medium. We create a pulse on our string by flicking the end of the string once. If we were to move the end of the string up and down repeatedly, we'd create a traveling wave, which has characteristics a pulse does not. As the pulse in figure 16.1 travels, each disturbed element of the string moves in a direction perpendicular to the direction of propagation. Figure 16.2 illustrates this point for one particular element labeled P. Notice that no part of the string ever moves in the direction of the propagation. A traveling wave or pulse that causes the elements of the disturbed medium to move perpendicular to the direction of propagation is called a transverse wave. Compare this wave with another type of pulse. One moving down a long stretched spring is shown in this picture. So with the slinky. The left end of the spring is pushed briefly to the right and then pulled briefly to the left. This movement creates a sudden compression of a region of the coils. The compressed region travels along the spring. Notice that the direction of the displacement of the coils is parallel to the direction of propagation of the compressed region. A traveling wave or pulse that causes the elements of the medium to move parallel to the direction of propagation is called a longitudinal wave. Okay. me get some water. Jeez. Boring. All right. All right. What's next here? Sound waves, which we'll discuss in chapter 17, are an example of longitudinal waves. The disturbance in a sound wave is a series of high pressure and low pressure regions that travel through air. Some waves in nature exhibit a combination of transverse and longitudinal displacements. Surface water waves are a good example. When a water wave travels on the surface of deep water, I'm gonna put on pants, man. I'm getting cold. In the morning, no lie. You set the night on fire. I'm still gonna be here in the morning, no lie. No lie. Oh yeah, I mean that's definitely a little bit better. The three-dimensional waves that travel out from a point under the Earth's surface at which an earthquake occurs are of both types. The wave function represents the y-coordinate, the transverse position of any element located at position x at time t. The propagation is longitudinal. And that's so A is longitudinal, B is a pulse moving to the right along the x-axis is represented by the wave function this, where x and y are measured in centimeters and t is measured in seconds. Find expressions for the wave function at bro, you literally just plug in a number. Okay. In this section, we introduce an important wave function whose shape is shown here. The wave represented by this curve is called a sinusoidal wave because the curve is the same. Imagine two types of motion that can occur. First, the entire waveform moves to the right so that the brown curve moves toward the right and eventually reaches the position of the blue curve. This movement is the motion of the wave. If we focus on one element of the medium, such as the element at x equal to 0, we see that each element moves up and down along the y-axis in simple harmonic motion. This movement is the motion of the elements of the medium. Okay, so it is important to differentiate between the motion of the wave and the motion of the elements of the medium. In the early chapters of this book, we developed several analysis models based on three simplification models: the particle, the system, and the rigid object. With our introduction to waves, we can deploy a new simplification model, the wave, that will allow us to explore more analysis models for solving problems. An ideal particle has zero size. We can build physical objects with non-zero size as combinations of particles. Therefore, the particle can be considered a basic building block. An ideal wave has a single frequency and is infinitely long. That is, the wave exists throughout the universe. A wave of finite length must necessarily have a mixture of frequencies. We will find that ideal waves can be combined to build complex waves, just as combined particles. In what follows, we will develop the principal features and mathematical representations of the analysis model of a traveling wave. This model is used in situations in which a wave moves through space without interacting with other waves or particles. Figure 16.A shows a snapshot of a traveling wave moving through a medium. Okay, figure B shows a graph of the position of one element of the medium as a function of time. Waves travel with a specific speed, and this speed depends on the properties of the medium being disturbed. For instance, sound waves travel through room temperature air with a speed of 350 meters per second, whereas they travel through most solids with a speed greater than that. Consider the sinusoidal wave from 16.8a, which shows the position of the wave at t equal to 0. Because the wave is sinusoidal, we expect the wave function at this instant to be expressed as y of x comma 0 equal to a sine little a x, where a is the big A is the amplitude and little a is a constant to be determined. At x equal to 0, we see that y of 0, 0 is equal to a sine a times 0 is 0. So that's correct. The next value for x for which y is 0 is lambda over 2. Okay, yeah, so wait. Notice that the vertical position of an element of the medium is the same. By definition, the wave travels through displacement delta x equal to 1 wavelength lambda.